Hello everyone, I'm Soumya Bhattacharya and today we are going to look at the implementation of visualizing a 3D Earth model within a mobile application. Specifically, we are going to talk about how we can render a spherical object, map geographic coordinates to that 3D space, and manage how user interaction works through a controller pattern. Moving beyond, a standard 2D map projection requires a fundamental shift in how we handle data and rendering. We do not simply place a flat image on a screen, we are creating a spherical mesh and mapping complex textures to it. Before we discuss the code, we must understand the geometry of the objects we are rendering. In computer graphics, a sphere is typically constructed from a mesh of triangles or polygons. To visualize a 3D Earth, we use a rectangular texture, usually an equirectangular projection of the world map, onto this spherical mesh. This process creates the illusion of a solid planet. However, the challenge lies not just in rendering the shape, but in interacting with it. When we build this visualization in a mobile app, we are dealing with a dynamic object. The sphere must rotate on its axis, respond to touch inputs for zooming and panning, and maintain a consistent frame rate. This requires efficient resource management. We use specific libraries to handle this heavy lifting of the 3D Earth, allowing us to focus on the application logic. The goal is to create a seamless user experience where the Earth feels like a tangible manipulative object rather than a static picture. In terms of programming, we can replicate a physical globe onto a 2D screen using the Flutter framework and the Flutter Earth Globe package. This process requires a fundamental understanding of coordinate systems, object oriented programming, and state management with mobile development. To place data on a 3D sphere, we rely on the standard geographic coordinate system. The system is the foundation of all geospatial software. It breaks down global positioning into two specific numeric values, latitude and longitude. Latitude determines the vertical positioning, measuring how far north or south a point is from the equatorial plane. Longitude handles the horizontal positioning, indicating the distance east or west from the prime meridian. In our software implementation, these physical concepts are translated into floating point numbers. A coordinate is simply a pair of double values. For example, a location might be defined as 28.6139 for latitude and 77.2090 for longitude. Understanding this is a crucial thing because our code does not understand New Delhi or London as names. It only understands these numerical vectors, two coordinate numbers on the globe surface with high precision. If we fail to input these coordinates correctly, the data mapping will fail and markers will appear in the ocean or the wrong continent. From a software engineering perspective, we need a robust architecture to manage the communication between our logic and the visual render. We utilize a variation of the controller pattern. In this context, the Flutter Earth Globe Controller is the core component that acts as the interface or the boss of the visualization. Controller is a tool used to interact with the Earth. Without it, the visualization component is merely a static display with no function. The rule for implementation is strict. We must create the controller before we can communicate with the Earth object. This ensures that the object lifecycle is respected. The 3D context must be fully initialized and the textures loaded into memory before we attempt to issue commands. If we try to add a marker or change the camera angle before the controller is ready, the application will likely crash or throw a null point exception. The controller acts as a single source of truth for the state of the globe. Now let's look at the initialization process in more detail. In the code base, the controller is initialized as Flutter Earth Globe Controller. This object exposes a set of public methods that allows us to modify the globe state at runtime. It is responsible for handling the queue of commands sent to the rendering engine. When we want to add a city, draw a line, or change the zoom level, we do not touch the UI code directly. Instead, we call a method on this controller instance. The separation of concerns is vital for clean code. It decouples the data layer, that is where our coordinates and cities lists live, from the presentation layer, which is the 3D view. This allows us to update the data dynamically, for example, fetching a new list of cities from an API and simply passing the data to the controller to update the view. without needing to rebuild the entire 3D scene from scratch. This efficiency is very essential for mobile performance. In terms of programming, to mark a spot on the Earth, we use a specific data structure known as the point object. This object encapsulates all the properties required to render a single marker. It acts as a container for our data. We use the controller.addPoint command when we are passing the structured object into the rendering pipeline. The point object requires several specific attributes to function. First, it requires a unique ID identifier, such as a string, which is one here, which allows us to reference, update, or delete this specific marker later. Second, it requires coordinates, which we pass as a global coordinates object containing our latitude and longitude values. Third, we define visual aspects such as a style attribute, specifically point style, where we define the color such as the color red and with the size such as 6 of the marker. Finally, we can add text labels such as London and set is label visible to true to ensure that the user can identify the location properly. A model application must be interactive. This introduces the concept of event-driven programming. The point object in our framework includes callback function to handle user input. Specifically, we have properties like on tap and on hover. These callbacks allows us to define specific logic that executes only when a user interacts with a marker. For example, in the code, when we define on tap, in the production application, this print statement would be replaced with a navigation logic such as opening a detailed view, displaying weather data, or showing photos of that location. The on hover callback allows us for desktop like implementations and interactions that provides feedback when the cursor or focus is over a specific point. This transforms the globe from a passive display into an active interface control. Moving beyond isolated points, we often need to visualize relationship between locations. In computer science, this is the domain of graph theory, where locations are nodes and the paths between them are edges. To visualize these edges on our globe, we use connections. These are animated arcs that span between two coordinates. We implement this using the controller.addPoint connection. Just like the point object, the point connection object requires structured data, a unique ID, example connection 1, a start coordinate and end coordinate. For instance, if we want to show a flight path from London to New York, we input the coordinates for both the cities. The rendering engine then calculates the shortest curve along the surface of the sphere and draws the arc. This creates a visually accurate representation of travel over a curved surface, which is fundamentally different from drawing a straight line in a 2D map. Static lines can be difficult to interpret in a complex 3D scene. To improve readability and convey direction, we utilize animation. The point connection object allows us to style the connection as dashed line and animate the dashes. By setting the type to point connection type dot dashed and defining a dash animate time, for example 2000 milliseconds, we create a floating effect. This animation is not for decoration, it represents temporal data or flow. The movement of the dashes from the start point to the end point visually indicates the direction of travel or data transfer. We also set animated on add true to ensure that line draws itself smoothly when it first appears. This smooth effect is handled by the render loop, which interpolates the position of the dash between frames to create fluid motion. This technique is essential for visualizing dynamic data sets like shipping logistics, network traffic, or migration patterns. The final layer of our implementation is customization. A generic globe may not fit the aesthetic requirements of every application. We have the ability to control the Earth's atmosphere and surface appearance for different effects. The rendering engine allows us to toggle between different texture maps, enabling us to switch from a standard political map to a realistic satellite visualization. Furthermore, we can customize the glow or atmospheric scattering effects to make the Earth look more realistic or more styled depending upon the design language. These controls are accessible via the Android Studio environment and the package configuration. We can also implement custom markers beyond simple dots, perhaps using icons or 3D models for more specific cities. This level of customization is handled by manipulating the properties of the controller and initialization parameters of the globe widget, giving us full control of the visual output. Finally, to summarize the implementation stack, we can start by initializing the Flutter Earth Globe controller within our main application widget. We then define our data, our lists of cities and connections using the point and point connection objects, ensuring all globe coordinates are accurate floating point values. We pass this object to the controller using add point and add point connection. Finally, we configure the visual style and interactivity callbacks to ensure the user can explore the data effectively. This process highlights the intersection of several computer science concepts such as geometry of 3D rendering, the data structures for geospatial information, the architecture of state controllers, and the logic of event driven UI. By using these elements, we can build high performance, visually informative 3D tools. Now let's move on to Android Studio for a detailed walkthrough of an example. Now let me walk you through a Flutter screen that renders an interactive 3D Earth globe using the Flutter Earth Globe package. We'll cover how the widget tree is structured, how the globe is controlled, how textures are loaded, how markers and routes are added, and how the UI controls the start and stop of rotation and resets the screen. Moving on to globe page.dart. This particular file has two main widgets. The first one being my globe, which is a simple wrapper stateless widget. It initializes a material app, applies a theme, and sets globe view as the home screen. Next being globe view. The core stateful widget, it handles the heavy lifting rendering of the globe, managing the controller, tracking state, and handling user input. We use a stateful widget because the globe is dynamic. We need to track changing states like is rotating, which is a boolean to toggle animation, has markers, which is boolean to enable or disable the reset button, point IDs and connection IDs, which are sets of strings to track added elements so we can clean them up later, and a controller, which is the engine driver for the 3D render. Moving on to the init state. The Flutter Earth Globe controller acts as a remote control for the globe. The widget paints the pixels, but the controller tells exactly what to paint. We initialize in the init state only once because we prevent performance issues during rebuilds. We set properties like rotation speed, zoom, and is day-night cycle enabled here. We do this thing once to ensure we don't reset the engine every time the screen updates. We cannot load heavy textures immediately because the widget might not be fully mounted yet. We use widgets bindings dot instance dot add post frame callback, which tells Flutter to finish the drawing the first frame and then run the load globe resources. This prevents crashes and makes the app start smooth. Moving on to load globe resources. In this function, we are dealing with applying textures and data. Once the frame is ready, the function runs to paint the globe. It consists of textures. It loads the day surface, the night surface. Think of this as wrapping a flat image around the ball. And it also loads the background for an immersive experience. Moving on to the function add demo markers. Here we add the markers and the connections. After loading the textures, it adds demo markers. Here there are 2 points, London and New York, and a curved connection between them. The key idea is everything has a stable ID so we can remove it later. The point object has the following attributes. First, an ID, which is a unique string, so we can remove or update this point later. Coordinates of latitude and longitude. Label and is label visible, which is a text near the marker. Point style, which gives color and size to the marker. And on tap, which is an interaction hook, which shows a snack bar here. We have another point of NYC, which has the same logic. This draws a route or an arc between the two coordinates and can optionally show a label. We store IDs in sets of point IDs and connection IDs. That's important for reset because the controller needs IDs to remove objects. Notice we call the set state at the end. This tells Flutter my state has changed and please rebuild the widget. We have set has markers true, which will enable the reset button in our UI. Without the set state, the UI will not update even though internal variable has changed. Now we look at the control functions. First, we talk about stop rotation. When a user taps the stop button, we need to do the three things. First, we tell the controller to stop the day-night cycle. The day-night cycle is what actually drives the rotation animation. The globe isn't rotating on its own. It's the cycle that makes it spin. So when we stop the cycle, the globe freezes in its place. Second, we update our internal tracking variables. We have this boolean called is rotating that we flip to false. We do this because the other parts of our app need to know the current state. The third we call set state. This is how we tell Flutter that something has changed and it needs to redraw the screen. Without this call, our button states will not update even though the globe has stopped. Finally, we show a snack bar. That's the little message that pops up at the bottom of the screen. It's just user feedback so that they know which action has been performed. We set it to disappear after 1 second because we do not want to hang it around in the screen. Moving on to start rotation. The start function is basically the mirror image to the stop function. We call the start day-night cycle on the controller and pass a duration of 60 seconds. This means one complete rotation, a full day on a virtual globe, takes 60 seconds. Then we flip our boolean to true, call set state to trigger a rebuild, and show another snack bar. One thing to notice here is that we are not checking if rotation is already true before starting it. We don't need it because our button is disabled when the globe is already rotating. The UI prevents double starts. But in other scenarios, we might want to add that check for safety. The 60-second cycle duration is a choice for demo for purpose. In the real life example, you might use other configurations as well. Moving on to the reset function. The reset function is more involved. This is where we bring everything back to the initial state. We remove the connections, we loop through a set of connection IDs and call remove point connection for each one. Then we clear the set. We remove the connections first because connection references the point they connect. If we delete the points first, we might have connection objects pointing to things that don't even exist anymore. It's cleaner to remove the dependencies first. Next, we remove the points. Same pattern, loop through our point IDs and call remove point for each and then clear the set. Now our globe is clean, no markers anywhere. The next step is to reset the zoom. We set the controller.zoom back to 0.5, which is our starting zoom level. Users might have zoomed in or zoomed out, and the reset should bring back to the default view. Last step is to handle the rotation. Here is a conditional check. If the rotation is currently stopped, we restart it. We want restart to truly restart everything, including getting the globe spinning again, which is the default state of the globe. If it's already rotating, we leave it alone. Finally, we update has markers to false and show feedback. The has markers variable controls where the reset button is enabled. There are no markers, there is nothing to reset, so we disable the button. This function shows something important about state management here. We are tracking IDs for everything we are able to add to the globe. Without the tracking, we will have no way to remove these things later on. Now let's look at how all of this is coming together, which is in the build method. We are using a scaffold with a black background. That's a canvas inside. We have a stack. A stack is like layering pieces of paper, one on top of the other. The globe goes down first, then a control panel sits on top of it. The globe widget is pretty simple. We pass in the controller we set up earlier and give it a radius of 120 pixels. The control panel is a card widget positioned at the bottom of the screen. We're using position with bottom 30, which pins it to 30 pixels from the bottom. We give it a left and right of 20 pixels for breathing room on the sides. Inside the card, we have a column with our time, a row of buttons, and a status indicator. The status indicator shows when the Earth is rotating and when it is not by reading from the is rotating variable. So it updates automatically when we call the set state. The buttons are where our control function connects to the UI. This is a ternary operator. If is rotating is true, we assign the stop rotation function. If it is false, we assign null. When you pass null to on pressed, Flutter automatically disables the button and applies the disabled style. So we get enabled or disabled behavior without writing conditional logic for the styling. Same pattern for start and reset. Start is enabled when not rotating. Reset is enabled when there are markers. The UI stays in sync with the actual state. The key takeaway here are use Boolean flags to track UI. Always call set state after changing state. Track IDs for dynamic elements so you can remove them later for reset. Use conditional callbacks to enable or disable buttons automatically and also give user feedback for their action. Here is the demo for the application. Since you can see that the day-night cycle is currently running, if we click on stop here, the rotation is stopped, which is the day-night cycle that has been stopped. If we again start it, it resumes back to the rotation. You can also see the markers of New York and London and a translation route between them. And if we click on reset, all of these markers are removed and rotation has been resumed to its original state. If we again stop it, it gets stopped again. So that's all for the demo. Thank you so much for your time and please feel free to ask any questions.